I just want to clarify. So the problem, like when a photon is hitting a person who is standing, who is not moving, who is at
Mm-hmm.
rest. So the equation should be like on the left side. The system of momentum should be like k plus p1 is equal to p2. But in the handwritten notes, it was written as k is equal to p1 plus p2.
So P1 plus P2. Probably, yeah, probably you are right because it should be like minus, there should be a minus term in the moment.
And next line it clarify it clearly returns k plus p1.
Mhm.
So I think
Yeah, probably
I
it was
just want to
just
clarify
it's a
there's a small
mistype. Yeah.
mistake. Okay, and the next question I had is like on the Compton scattering, um, like so in the system of equations, so where we see the momentum of the photon, the momentum of the incident photon.
Mm-hmm.
So in a 4D vector space, at least four vector notation,
Mm-hmm.
we have the first vector as h bar omega by c. So that is
Yeah.
fine. That is a e by c. So that
Mm-hmm.
is e by c. But then the momentum of the photon, like the p vector is written as h bar k k vector, and that is equal to omega by c unit vector k unit vector.
Yeah. So basically, maybe just to because I just to clarify this one. So usually, before to complete your question, so we define the k vector as the magnitude of k times k unit vector. And this magnitude of k, that what we can write like h cut omega over c.
So that is like see that is the yeah h cut omega by c h cut omega by c.
So if
So
you
this
see
for
the
the photon, this is like what I'm always getting confused is like when you're writing the momentum for a photon in a
Mhm.
four vector space, the first component e by c is fine, but the
Mhm.
second component the second component like what I was always what I'm always confused is like I understand for a photon it should be zero. The second cause because there is no mass, so it should be zero.
Not zero because it will be like if I write the equation of motion, I mean the Einstein equation, E square equals to P square over C square plus M square C to the power 4. So if we consider photon, then this mass will be zero because this is the rest mass. So it will be E is equals to PC. So now if you want to write the 4 vector, so let me click this on. So if you write the 4 vector of the photon, let's take mu notation just to clarify this is a 4 vector. So the zeroth term will be the energy over C, which will be nothing but h cut omega over C, just converting doing the calculation, and then there will be k vector. So this k vector, because photon had no rest mass, but it also has a momentum, and that momentum we define in terms of k vector.
That's what I want to understand.
Yeah,
Yes, the photon will have some yeah. When you say photon has some momentum, can a massless object can have momentum?
massless. Yeah, I mean momentum is like suppose if you consider a like when a beam of light, a photon is coming to you, if you consider in terms of wave, or if you consider in terms of particle, so like photon is moving, right? So any moving object has some momentum, otherwise it cannot move. So it does not have a rest mass, but it has some momentum, and that momentum is come because of in this case not because of the rest mass, but because E is equals to square. But you have this relation, right? So you can get from here E is equals to PC. So that's what you need
So,
to.
like again, the definition of momentum will be like, sorry, the classical definition of momentum is, I suddenly am forgetting actually. The classical
Yeah. So
definition of momentum is like impulse, right?
something different. Impulse is force per unit time. That's called impulse. If you have a if you apply some force per unit time, I mean in a particular 1 second of time, that gives you the impulse. So momentum is basically in this case actually at least the momentum is coming from the energy. If you just convert this one, this momentum and this energy.
Okay,
So
okay. So
so
maybe like we can say like any object that has some energy will have momentum as well.
yes, yes,
It need
yes.
not have rest mass,
Yeah.
but
So
if there is a energy, it will
it
have
has a
momentum.
rest mass. Down the ds and also like e square c square equals to e square. Sorry, minus n square c to the power 4. So you can get some momentum. Is if I take this term is square root of e square over c square minus m square c square. Yeah. So also if you remember in the last class we defined the four momentum. The four momentum was defined in this way. The first term was m naught c over square root of 1 minus v square over c square. And then the vector term was written like m v square root of 1 minus v square by c square. And this one, what is written here, it is for the massive particle. Otherwise, you don't get this quantity here. This m is not. But when you consider photon, as I mentioned, the photon is kind of a peculiar particle. It has some own nature. So in that case, you need to consider, you need to think from this Einstein relation.
So like when we did the four vector for momentum, right? I'm just going through the notes again. The four vector for the k vector. Yeah, the k vector is defined as omega c comma k vector. Okay, the four vector.
Yes. So this k comma is coming from this omega over c, that will be the p, because also we can write p is equals to I guess omega over c or omega time, something like this. So this is your vector component and your zeroth component, that will be your again omega naught over c. This is just your magnitude one.
So, sorry, how did you derive that? Like the k vector is equal to omega over c k
So
caret.
we have to maybe start with again from so we need to start from the wavelength, de Broglie wavelength, lambda equals to h over p. This is one of the relation. And second thing we need to consider E equals to PC. I just trying to write down what is the formula we need to calculate, and also we can write E is equals to h cut omega E over c. So h cut omega over c. Yeah, this is I think this notation E equal P is, momentum equals to energy by time. So we can write E equals to PC for photon, and the energy term you can write h cut omega because we know energy E equal, this is Einstein notation, E equals to h omega. So if you just put it here, yeah, so that way h cut omega over c, and if you want to the vector, then this is the magnitude, and you need to give the direction in which direction the photon is moving.
Gotcha. So in the case of like photon, when we decide like when we work on the four vector for the photon, we have to think about the de Broglie wave so that we
Yeah,
can think
we can start from here
matter.
because this is the equation where it's a equation between the energy wave and particle nature, because this side is a particle nature, this side is a wave nature. That's what photon also had, right?
Gotcha. Okay, okay. I think I'm clear now. I think yeah.
Okay. Okay, so let me just clean this board. And in last class, we mostly discuss about the relativistic kinematics. So today, what I am planning to do, I will introduce the symmetry, because as I told you already in the email that this I will divide the class in two part, or it needed three part, because the symmetry is very important. And whenever we even we try to understand in terms of mathematics or in terms of physics, In both the cases, symmetry will come into picture. So we will take some time, go step by step instead of moving too slow, too fast. So what I will do. So today first let me start with, yeah, again the fundamental force in nature. So and then we try to understand how for different fundamental force of nature like electromagnetic cases, where the QED, quantum electrodynamics, come into picture. And then we have a one kind of symmetry. Then when we go to it's basically we call it U1 symmetry. When we go to the strong interaction, there is SU2 symmetry. When we go to the weak interaction, there is SU1 symmetry. So this kind of terminology we use very often. So it will be, I guess, it will be good at least for once to make a clear picture whenever we talk about the symmetry in different cases in different physics, how the concept of symmetry come into picture. So let me also I am thinking today to discuss a little bit about Feynman diagram, at least the graphical way, and then later we'll try to understand into more physical way how one can do. So let's consider today's class is like a uh, basically Feynman diagram for baby, because to understand Feynman diagram mathematically we need to do a lot of mathematical calculation. So that we'll probably do later. But like the Feynman diagram was one of the greatest achievement in 20th century physics, where uh, there was a particular time when the concept of QED and QCD it was almost about to die. It was became more complicated because there are a lot of mathematics, some abstract algebra, and for someone like us who are laymen, we don't understand much mathematics. We are mostly concentrated on physics. For us, it was very difficult to understand all these physical phenomena. Then Feynman come up with a very intellectual properties, and he considered, okay, we can do one thing. We can try to graphically understand with all the interaction which is very often we use in our nature. Like if I consider electromagnetic force, so is visible this color or probably
Yeah,
not?
yeah,
It
it
is.
is
It
okay,
is.
visible.
So we define this physics as a QED. So whenever we try to understand, let's first try to draw one very basic and simple picture of QED that consists two electron. So what we will do when we try to draw the Feynman diagram, we first always, at least for my reference, I consider always time in this direction. And whenever I consider particle, so for any kind of fermions, for the fermions, I will use uh, a line with arrow. So this arrow will be representing the direction of the momentum of the particle. And when I consider bosonic particle, I will use this wave notation. Like when I consider electron, I will use this notation. When we consider gluon or photon, all the exchange particles which are responsible for the exchange, which is basically bosonic particle, we will use either this wave notation. And also, just to keep one thing in mind, whenever we try to draw the Feynman diagram, three important conservation law we should keep in mind. One is called baryon number conservation. I'll talk in details about what the baryon number means. Baryon number conservation. This is one thing. Whenever we try to draw or try to understand the Feynman diagram, one thing we have to understand the baryon number in each of the node. What I mean by node here, the interaction point where I consider the baryon number should be conserved, then lepton number should be conserved. So in the beginning class we were talking about lepton number, baryon number, but we will talk in details later. And charge should be conserved. So these are basically very three fundamental conservation law we should keep in mind when we will try to draw the Feynman diagram. Later, we'll try to understand how one can calculate all the mathematical terms in all the different points. But for now, for this our understanding, let's what I'm trying to say. Let's two electrons. So the two electrons coming and they interact with each other, and by exchanging of by exchanging of photons. So at this point, there will be some interaction here, and then we will get electron back. Okay. So now what will happen here? In this case, if I consider this electromagnetic one photon, that will be that will be create here at this point, and yes, this photon, this is basically a virtual particle. This particle is just exchanging between these two electrons to to help to understand this electron which is reached here, that there is